we'll begin now. Thanks everyone for joining again. My name is Ryan Magruder. I'm an analysis services engineer here at Abaqus Systems. I started with SOLIDWORKS Simulation before learning Abaqus, so I'll be giving some tips and tricks along the way that I think will be useful for other people making that transition. The content that we'll be looking at today, the title SIMULIA Abaqus, First Steps for the SOLIDWORKS Simulation User. We also have a few panelists here today. Tim Milo, our SIMULIA product manager, and Paulo Olmos, another one of our analysis service engineers, and they'll be sticking around to help answer some questions at the end. For more of our video content, you can use that link below. You can see past webinar Wednesdays, and a recording of this webinar will also be uploaded after it's finished in case you want to review anything. And in addition to the video content that we have here, like the webinar Wednesdays, we also provide some more content on our website. You can visit for self-help resources, blogs, technical support for all of our products. You can also find more schedules there for upcoming Webinar Wednesdays and training courses that we offer online or in person at one of our training facilities. If you're looking for more personalized assistance with your application, you can also contact us for mentoring or consulting services as well, which is what I do here. For the services, what we provide is a review of your application and then a development and execution of an analysis. We can deliver the results as a report if all you're interested in are the results and the setup details, or if you'd like, we can set up a mentoring session where we take you through the analysis to not only show you how we set it up, but to give some insight on why we made some of the decisions that we made. So it's a great tool if you're looking to get something set up initially and then maybe run some more studies down the line. We also offer shorter mentoring express sessions, which are just 3-hour live sessions, either online or in person, where the topics are just driven by what you bring to the table. So it's useful if you just have something you need maybe another set of eyes on, just a couple hours with one of us to just kind of go over the study, see what may be the best way to move forward. Those sessions are great for that. So if you are interested in any of those, definitely let us know. So taking a look at our solutions portfolio now, you can see that Abaqus is going to fall kind of in the same area as all of our other simulation products. It's going to be a validation tool that we use to either improve our designs through simulation by setting up simulations with real-world conditions. You can also replace destructive testing with this virtual testing. And we'll take a look at kind of our family of simulation products here. And so whenever you're starting up a simulation, it's important to know that each product is tailored for a specific application. So picking that right tool is definitely the first step to any analysis. For rigid body, kinematics, or injection molding simulation, we have the SOLIDWORKS Motion and SOLIDWORKS Plastics packages. For fluid flow analysis, including electronics cooling and HVAC, the SOLIDWORKS Flow Simulation package offers a very robust and powerful solver. But if you're interested in structural mechanics, you have those two options. You have SOLIDWORKS Simulation or SIMULIA Abaqus. So just like motion, plastics, and flow simulation, SOLIDWORKS Simulation is built right into SOLIDWORKS, so it's easy to pick up, easy to learn. You're dealing with that same interface that you're already familiar with. But for Abaqus, it offers enhanced capabilities for implicit solutions with its standard solver, and then there's also an explicit solver for highly dynamic problems that cannot be solved in SOLIDWORKS. The question can be, though, when should I move to Abaqus? And if you're considering Abaqus, if you're someone in here who's a SOLIDWORKS simulation considering it, that's definitely one of the questions to ask if you do have both. Does the analysis problem that I have require Abaqus? It's not always going to be a straightforward decision, but we definitely do have some general recommendations that we'd like to share as part of this. And the general basics are, it's going to help you out if there's increased complexity, if you need an increased level of realism. And that kind of brings us to these 4 main points that we usually consider when we're deciding, at least on the services side, whether a problem is best suited for SOLIDWORKS Simulation or Abaqus. And the first one there with contact. Anyone who's set up a problem in SOLIDWORKS with a large amount of contact knows how difficult it can be. Not only do you have to go through all the trouble of selecting all of the faces you need, maybe splitting the faces to make sure the contact goes through, it can also be difficult to get the solver to run if you have a large amount of contact. It's something that we know is difficult, but Abaqus is going to attack that with its either general contact solver or just a more robust and advanced surface-to-surface contact. The general contact is as close to a one-click contact feature that you're going to get. The solver is also just much more efficient and successful at solving these types of problems with large amounts of contact. So that's definitely a big one. Rapid events, either drop, impact, or shock, are definitely ones where it's pretty easy to know you're going to need to switch over to Abaqus. The dynamic or at least the highly dynamic events in SOLIDWORks, the capabilities are a bit limited. There is a drop test study option that you can use with an explicit solver, but the amount of control that you have over it is very limited. The Abaqus explicit solver allows you to simulate a wide range of events, like this one on the right here of a golf club impacting a ball, something like dropping a smartphone, or even something like simulating a full car crash. Those are all possible, and it's a very powerful solver in Abaqus. So this is a pretty easy one to know when you need to move over. Large deformations may be a bit more of a gray area. Aside from being able to handle just more pronounced element distortion, Abaqus also has adaptive meshing techniques for problems like the one on the right there, where the elements become so distorted that the simulation needs to replace the elements with new ones, and you can map those old stress results over them. This tool makes problems like the one on the right a lot easier, especially when you have large deformations, high strain, stuff like that, where SOLIDWORKS is kind of reaching the end of its capabilities. And finally, another one like rapid events that is a bit easier to know when you need to make that transition, multiphysics problems. SOLIDWORKS does have FEA and CFD packages, obviously, and there's certain ways that you can kind of use the two to interface with each other. But there isn't a full coupled analysis like something that Abaqus can do, something there on the right. There are built-in electromagnetic and coupled thermal structural capabilities. There's a CL solver for explicit that allows you to track the bulk fluid movements, washing, structural interaction. It's important to note that for problems like this, Abaqus is just going to go about it by capturing the fluid potential, not the turbulence. So it's great for problems like the one on the right, but if you need full flow simulation, you can couple another CFD product with Abaqus as well. So with all that said, let's take a look at the agenda for today, what we're going to go over. The main tool that we'll be highlighting for SOLIDWORKS users interested in incorporating Abaqus is the SOLIDWORKS Associative Interface for SIMULIA Abaqus. We'll use this tool for a case study of a syringe analysis starting from setup in SOLIDWORKS all the way to post-processing the result in Abaqus. You can see the final result that we'll be working there towards on the right. The goal that we'll be looking at is trying to measure that reaction force of pulling that syringe out. You can see it playing there. We'll also be taking a look at an alternative method, just briefly, which is the SIMULIA Abaqus Translator for SOLIDWORKS. It's another method, and we'll kind of go over some of the pros and cons of it and how it differs from the Associative Interface. So the Associative Interface. The Associative Interface is a one-click tool that you can use to export your SOLIDWORKS models into Abaqus. It creates a link between the two so that model changes that you make in SOLIDWORKS can be pushed right into Abaqus without making you reset up your study again. In this way, you can really harness the power of both softwares. You can do all of your modeling work in SOLIDWORKS. You can do all of your analysis work in Abaqus. And there's no extra setup or kind of headaches to go through. It's just going to act like it's taking that model directly from SOLIDWORKS. And as long as you're not making drastic changes to the model, there's a minimal amount of rework that you have to do with the analysis itself. To take a look at this, we'll be investigating this case study here to the right, which is the syringe that you've kind of seen some pictures of. The goal here will be to develop a parametric process for evaluating the impact of the design changes and the force required to pull the syringe. For the analysis setup, you can see this list that we'll kind of work through here. And each one of these items in the list is a module in Abaqus. And modules are what we'll get into a bit later. They are basically individual parts of Abaqus that we can use to access different features. And if you just work your way down the list, just like you would in a SOLIDWORKS simulation feature tree, it's a pretty tried and true way to go about setting up your analysis. So with all that being said, let's move over to the software and we can get started here. So this is our syringe. You should all be able to see the SOLIDWORKS files now on the screen. If you don't, just let me know through the chat. Let's take a look, kind of investigate the syringe here. I'm just getting an idea of what we're working with. We've got three parts. We've got this outside barrel, we've got the plunger, and then finally we've got that stopper there down in the middle. If we take a section view of this, we can kind of get a better idea of what we're looking at. And if we zoom in here, we can see that there's some interference going on between the stopper and the barrel here. And we can kind of highlight those with the interference detection in SOLIDWORKS. And if we hit calculate there, we can see those. So we've got this bit of interference here down at the bottom. We've got kind of the largest amount that we'll be working with, at least the amount that we're interested in here on this, this bumper on the outside, and then just a bit at the top there to stabilize it. And so immediately by looking at this, we can kind of make some decisions right off the bat, knowing the analysis that we're trying to do and what package we're going to need to look at. And so with anything with interference, we know that we're going to have to resolve that interference before we want to start that analysis. And so we're going to have two steps right off the bat. We're going to have to resolve that interference, and then we're going to have to pull that plunger out. And so knowing those two facts immediately lets us know that we're not going to be able to do this in a linear analysis, at least in SOLIDWORKS. In SOLIDWORKS, that linear analysis is going to step through that interference from the beginning to the end. And if we wanted to then pull the plunger out, if we put a prescribed displacement on the plunger and tried to pull it out, it's going to try and go through that in the same steps as that interference. So we know this can't be done in linear. In a nonlinear analysis, if we wanted to do this in Abaqus, it's possible that we could do it, but one of the limitations of a nonlinear analysis in Abaqus is that those shrink fits need to be resolved in the first step. And so if we had a problem where there's a large amount of interference that needs to be resolved, something where you're going into the plastic range of materials for a shrink fit, you're going to have a lot of trouble with those kind of analysis in SOLIDWORKS, just because that has to be resolved in the very first iteration. So we can't step through it, we can't reduce the time step, anything like that. And it can make problems like this difficult. So we know that we need to go nonlinear. We know that we probably may run into trouble if we try and do this in SOLIDWORKS. So we make the decision here that we want to move this into Abaqus. So let's take a look then at the model here. So all of our model preparation we can do right in SOLIDWORKS. That's kind of the benefit of these workflows, is that we can harness the modeling power of SOLIDWORKS with the analysis power of Abaqus. So looking at this, one of the first things that we know that we're going to need to do is cut it into quarter symmetry. The model can be cut that way, and we can cut down on a lot of our analysis time, and we can do this right in SOLIDWORKS. And so we've got this set up already in a preset configuration, and we made that just with a assembly cut here. And if we take a look at that, that can kind of bring us to our first thing that I wanted to point out of the associative interface, which is this propagate features to parts option down here. So we check this on, and what checking this on does is it's going to create a feature at the part level that's going to change the part itself. So it's not just a cut that we're making in the assembly. If we actually open up one of the parts here, we're going to see that the part also has that cut introduced here. And that's important because the associative interface is actually going to pull the last saved version of the part that you have. It's not going to pull the part as it currently exists in the assembly. And so it's important that your parts are actually saved in the configuration that you want them to be pushed into Abaqus. That also means if you had multiple configurations of a part, you would need to have those parts saved in those appropriate configurations before you do that export. So just something to point out there. Definitely, if you had a lot of bolts with different configurations, it's something you're going to have to consider as you're kind of setting up the configurations of it. So that's why we have that propagate feature to parts option checked on. And now that we do have it checked on, we've made all the changes that we want to make in SOLIDWORKS, at least for now. And so we can go through and push this over to Abaqus. And we have the associative interface turned on. It's just going to look like this little toolbar up here with this button. And like I said, all we need to do is click this button to push it over to Abaqus. And so we've got Abaqus running in the background, and we can click this here and push that over. So we open up Abaqus, and we can immediately see here that the model has been pushed over. We're in our assembly module. We've got all of the parts that we wanted brought over, and that's as easy as it is. It's just a one click, and it's going to be brought over. If you take a look at the message area down here, you can see that message indicating the creation of those parts and instances. And now let's take a moment and just kind of look at the Abaqus interface. So if you are a SOLIDWORKS simulation user, you've never used Abaqus or never seen it, we should hopefully just be able to give you kind of a quick breakdown of the interface here. The tree that you see over here on the left, you can treat it a lot like your SOLIDWORKS simulation tree. You're going to have everything that you would need to, if you wanted to create analysis features here. And just like the SOLIDWORKS simulation tree, you can kind of work your way down it the same way that you would do in SOLIDWORKS simulation. Over here on top of the graphics area, we have what is that module selection. So this is what I mentioned earlier that we'll be kind of working through as well. So all these areas that you see here are also available here through the module selection. And we'll kind of go through each one of these as we're going through and setting up the analysis. As you select different modules, you'll also see that your drop-down options are going to change. This toolbar to the left of the graphics area is also going to change, and this is where a lot of the common features that you may want to use are going to be situated. So it's always important to remember which module you're in. If you're looking for a feature, just make sure to transition to the correct module there. So let's take a look, and we will start out by setting up the analysis. So just like in SOLIDWORKS, we'll just start from the top of the tree there. We'll start from the top module. This is the part module. This is what you would use to actually design parts if you were going to be using Abaqus as your main CAD feature as well. It's not totally applicable for this scenario since we have imported the parts actually. So there's nothing that we need to do here. We've already imported all the parts. We can select from what model we're working from here, and then we can pick a part that we would need. So they're already designed, so we can move on from that part module. We won't need to do anything there. The property module is where we will create and assign materials. So unlike SOLIDWORKS, Abaqus does not have any built-in materials, so they will either need to be generated, copied, or imported every time. So let's start out just by creating a standard PBT material. We can do that from the tree over here. We can right-click and hit Create. We can also do that from these toolbars here. Each one of these on the left here is a kind of a tool that you can use to create features. And then on the right, you have managers where you can see any material that you've created, sections, basically anything that relates to that feature. You can manage it by seeing them, editing them, changing, in which step they appear. And we'll take a look at those in more depth a bit later. But let's start out just here with a basic material. And if we click that, we can see the Edit Material dialog box here. So we can assign a name to the material. We'll just call it PBT. And then we can assign material behaviors to these. Material behaviors can act as mechanical models, thermal models, basically anything we need to accurately describe the behavior of the material. And as we kind of scroll through here, you can kind of get an idea of all the different material models that Abaqus offers. For this one, we're just going to go with a simple elastic behavior. We'll set a Young's modulus, and as we're entering this, another important point to point out here is that Abaqus is inherently unitless. And so any number that we enter in here, we got to make sure that all of our units are consistent. So the assembly that we exported from, at least in SOLIDWORKS, was set up in millimeter gram second. So everything that we're entering here into Abaqus needs to follow that same unit convention. So we'll be entering these in megapascals. Once we've created it, we can then see it pops over here on the right. We can see that PBT there in our materials folder. And now we'll go ahead and create a rubber material for the stopper. So instead of creating a new one from scratch, I'd like to highlight one of these tools that Abaqus has. It's this Copy Objects tool. And we can use this to copy things from other models into our current one. So this is definitely useful if you've got complicated materials that you need to recreate and you don't want to have to go through entering all the data in and over again. We actually have two models set up here. These are finished models of the webinar that we'll be going through today. So we can use that Copy Objects tool to copy some materials from those. In this Copy Objects dialog box, you can see you select the model that you want to copy from. You can see everything that we can copy here. So we can copy parts, instances, materials, things like amplitude curves. It's a really robust tool and useful when you've got things that you already need, maybe a database of materials or something contained in another model, and you just want to move that over. And if we expand that material section here, we can see we've got those two materials, PBT and rubber. We'll just select the rubber. We'll choose that we're copying it to that webinar model, and we'll click OK. And now we can see that rubber pop up over there. So let's edit that and just take a look at that rubber real quick. Same dialog box, we can see that we've added that hyperelastic material behavior for the rubber. If we look in here, that's under that elastic folder under mechanical. For the strain energy potential, we've chosen Mooney-Rivlin, and then we've just entered in some material constants there for the rubber. So now we have our materials. Just like you can have materials saved in a database in SOLIDWORKS and you need to assign them, we'll need to assign them to these parts. And the first way to do that is to actually create a section. And a section is that next option here down in the toolbar. Sections are what we can use to define what type of geometry we're dealing with. And so just like in SOLIDWORKS, so you can right-click things in the tree, maybe say treat as a beam, treat as a shell, things like that. That's kind of the definition that we'll be using for sections. And you can kind of think of it that way. So for this section, we'll just call it PBT. We'll let it use the defaults of a solid. And then in our edit section dialog box, we'll choose PBT as that material that we'll assign to it. And we'll just do the same real quick for the rubber. So now we have our two sections. We've got our two materials, we've got our two sections with those materials mapped to them, and we will apply those sections down to our bodies. So if we switch back to the barrel here, working our way down this little toolbar tree again, we find that Assign Section button, and if we hit Assign Section, we can go ahead and select the region that we want to assign that section to. Now, before we hit Done here or hit Enter, I'd also want to note that when you're going through a lot of these commands in Abaqus, if you're selecting things to apply certain features to, you're going to get this box down here for creating sets. Sets are just grouping of regions, nodes, faces, edges, anything that you're essentially selecting at the time. And naming these is kind of good practice, and it can help you keep things organized. And you can also use these to reference later. So let's just go ahead and just name that as that whole body, since that's what we'll be picking there. And then we get this Edit Section Assignment dialog box, and we'll just pick PBT there. And we'll just go through that real quick and do it for the plunger and the stopper. All right, so we've got all our materials defined, we've got them applied to sections, and then we've got those sections applied to our geometry. So that's it for the property module. We're all done there. We've got all of our materials set to go. So let's move on to the next item in the list. Our assembly module. So this, again, is an area like the part module where we're not going to need to do anything at the moment. We've already got our parts created, and by default, all of those parts have been brought into our assembly in instance. If you had more parts that you wanted to add for some reason, this is where you would insert them into your assembly just like you insert parts into an assembly file in SOLIDWORKS. So you can use this Create Instance button and then pick which parts you want to bring in. And from there, you can move it around in the assembly with the Translate, Rotate tools, all that good stuff. But for the moment, all of our parts were brought in automatically with the Associative Interface, so we're already set and we're good to go, and we can move on. So this brings us to the step module. So steps are definitely one of the kind of the first things that is going to differ a lot from a SOLIDWORKS simulation that you'd set up. In Abaqus, you can essentially break up the problem history into these different steps. A step is a convenient phase of the history. It contains a discrete set of boundary conditions with a defined analysis procedure. So this analysis procedure can be changed between studies from static to thermal to dynamic. It essentially lets you stack on different physics on top of each other in the same analysis, and it's a really powerful tool in that way just because it lets you put models through one loading condition and then another, and it gives you a lot more functionality over SOLIDWORKS, and it's what we'll use to kind of accomplish that goal that we had initially of resolving that interference and then moving that plunger out. So we'll start off just by creating a new step. Again, it's just that top one there in the toolbar. You can also come over here in the tree like we did and hit Create there, so we'll do that. We'll name this step Interference Frictionless, because we'll just be resolving that interference without friction initially. And this is how we'll go about doing it. So the first thing that we'll do is resolve that interference, and then we'll create some additional steps. In our step dialog box, we're just going to want to choose which step we're going to insert it after. So you're always going to have this initial step here, which is just where everything gets initialized, and then you move on with the analysis. You can see all the steps that we could add here, all the procedures. If you wanted to do dynamics, explicit, stuff like that. You also have your frequency options here under linear perturbation. But we'll just choose static general for the moment, so that's all we'll need, and we'll go into this step dialog box. So when you're creating a step, a couple things here on this basic tab to take note of. The time period is just the time that your step is going to go over. Since we're just in a static analysis, this is just pseudo time. If we were in dynamic, we may actually need to take that into account, but for the moment, we can just leave that as 1, as it's just pseudo time. We don't need to worry about it. Nonlinear geometry. So this option, if we check this on, essentially what we're doing is moving between what you can think of as a static or a linear analysis in SOLIDWORKS into a nonlinear analysis. So this is going to take into account changing boundary conditions, nonlinear material curves, all that kind of stuff. And checking this on is going to keep it on for the remainder of the analysis. Incrementation, so this we can control how it's going to increment through. Again, this is something that we couldn't do for that interference in SOLIDWORKS. So we'll just set this up as 0.1 for now. We'll leave the others at default. And then on the other tab here, you have a bunch of different options where you can control the solver. For the moment, we're going to switch the matrix storage to unsymmetric. If you do have things like contact and friction, which we'll eventually have, it can be a bit more cost-effective to run this in unsymmetric, and so we'll switch that to unsymmetric for now. and we will click OK to create that step. And with the step creation there, you can see it created under our tree, and we can go ahead and create a few more steps here. So once our interference is resolved, what we're gonna do is change the friction value so that we have some friction while we're dragging that. For incrementation, we will put this on 0.2. And then our final step here will be where we're actually pulling the plunger. And for this, we're going to leave the initial at 0.5, and then for the maximum, we're also going to put 0.5 just because we want to get those full steps taken out. We don't want it to jump ahead too much. We want to kind of see those full results as it's going through. So those are all our steps. We're all set up now and ready to go from the step manager, and we will move on to interactions. So interactions are built up in a similar way to how we did the properties. If you remember the properties, first we created the materials, which have the properties of each material, and then we assign those to sections and finally assign those sections. So when we're building up interactions, the first thing that we'll want to do is actually define the properties of those interactions, define how the parts are going to contact each other, and then we assign those properties into an actual interaction itself. So we'll start off by defining an interaction property. We can do that through the tree here or on this button here. You can also get these through the drop-down menus at the top. There's a lot of different ways to get to each of the features in Abaqus. So this is our first interaction. So we're going to want one interaction with no friction for that first step, and then we're going to want another interaction with some friction as we're pulling that plunger out. So the first interaction that we'll create is just going to be interference frictionless. We'll just select contact as the contact type. We have a bunch of other interaction properties that we could use. And then in our contact property dialog box, it's going to look, again, a lot like that material dialog box where we can assign different behaviors to this contact. In this case, we'll add a tangential behavior, which will leave us frictionless, and just a normal behavior there. We'll then create our friction. So we'll name this friction efficient 10. Same thing here, we'll add that tangential behavior, but instead we'll choose penalty and we'll set a friction coefficient of 0.1. We'll also add that normal behavior there. So now we've got our interaction properties. The last thing we need to do before actually creating the contact is create an initialization feature. And we can do that here. And this initialization feature is going to tell the software what to do right at the beginning there, especially for these initial overclosures. So we're going to choose treat as interference fits, and this is going to resolve that interference. Again, this is just a property, and so we'll assign this to contact later. And now that we have all of our interaction properties, we can go ahead and actually create that interaction. So we can do that here with this create interaction button. We get our dialog box here where we're just going to name this general contact. And this general contact tool, if you are familiar at all with Abaqus or if you've heard about it, this general contact is one of those kind of selling points on it. It's this easy contact option, definitely one of the major benefits over SOLIDWORKS. It needs to be assigned in the initial step. So just something to note there, when we were in the other step, it wasn't available. So in our initial step, we just choose that general contact option, and we get the general contact option dialog box. So we can just leave this as all with self, which means it's just going to apply it to everything. And for our global property assignment, there are those properties that we created earlier. So we can choose that frictionless property just to start off. And then for our initialization, we're going to go into the initialization dialog box, choose it just for global, self, and there's that property that we created. We'll move that over, click OK, and now we've got that initialization. We can hit OK, and that's all there is to it for interactions. We now have basically what you would think of in SOLIDWORKS as a global no penetration contact, which is going to resolve those interference steps initially. So very easy, a lot more straightforward than you would have to go through in SOLIDWORKS, and definitely very powerful as well. The last thing that we'll want to do for these interactions is to change that friction value. So to do that, we can use these managers here that I pointed out a bit earlier. If we click on this interaction manager, what we'll see is what you'll see in a lot of these managers here. We'll see that feature that we created, and we'll see what state it is in each one of these steps that we have. And so you can use this manager to, if you wanted to deactivate that contact in a certain step here, you could hit deactivate, and it's not going to be active anymore. You can use this for loads. You can use this even for things like parts if you want to remove something from the study. And so you can edit a lot of your properties here right from this manager. In this case, we're just going to select this box here under Change Friction for the property we want, and we're going to hit Edit. That brings up that same general contact dialog box that we saw earlier. And then from here, we can just change this to friction coefficient. And now once we've made that change, you can see it's going to pop up as modified. And everything in here is going to work left to right. And so it's created here. That whatever has been created is then propagated. And since we modified it here in this change friction step, it's propagated then into the pull plunger. So if we edit it here, we can see that that same change has been made there. So everything is going to work from left to right there, and that change that we made will get propagated over to the next step, which is where we want it. And so that is it for interactions. We're all set up and ready to go there. We can move on to the load module, which is a lot more similar, at least, to SOLIDWORks. You can apply loads here. You can apply boundary conditions. It should be a lot more familiar to anyone who's worked a lot in SOLIDWORks simulation. We'll start out just by creating that quarter symmetry that we need. So we'll create a boundary condition, and we'll just name this Y symmetry. For the step, we're going to choose that initial step since we want this to start an initial and then be propagated throughout the entire analysis. And we're going to choose that symmetry option there. Once we hit continue, we select the faces that we want. And we'll select that Y symmetry. And we'll do the same real quick for the X. So once we have our symmetry defined, let's go ahead and make a fixture to hold the barrel in place here. So a fixture, we can do the same that we just created the symmetry from. We can go to a boundary condition. We'll just call this fixture. And from the initial step, we're going to select this displacement/rotation option. So this is going to let us control the displacement or rotational degrees of freedom on all of the entities that we select. And so if we select this face here, and we can just name this top of the barrel, what we'll see then in this displacement dialog box is we can select which degrees of freedom we want to have control over. And so if we select them all, essentially what we're doing is controlling every single degree of freedom of every node on that face. And so if we do that, and then we just set it to 0, it's going to act as a fixture. And so that's how we would create a fixture in Abaqus. So not a tool named that like in SOLIDWORks, but we can do that with those displacements there. And if we go into the manager here, it's going to look a lot like that interaction manager where we have all the features that we've created, and then you can see what they're doing in the different steps. And if we take a look at that fixture in this interference step, we can see that all those values have been set to 0. So in your initial, you're just initializing that feature. You don't have any control over the values. But here, if we leave these at 0, which they will be by default, it's just going to hold that in place and essentially act as a fixture. And you can also change those values to prescribe displacement, which is what we'll do next to describe that displacement where we'll be pulling the plunger out. So just like in SOLIDWORks, we'll want to pull that plunger out using a prescribed displacement so that we can measure the reaction force. And so now before we do that, we're actually going to move back over to the assembly module to kind of point out another one of those nice tools that Abaqus has that makes it a bit easier. And so in SOLIDWORks, we would just pick that face and prescribe that displacement on that face to move it out. In Abaqus, what we're going to do is actually create a reference point. Reference points are points in the model that you can couple to the surfaces to basically use as handles to move the geometry from. It also lets us measure the reaction forces from that single point instead of having to select all of the nodes on that face. So using this kind of workflow is definitely something that we would recommend, and it's powerful, and that allows you, to control whatever you want with a single point. And after we create that reference point, we'll just look for it here. We can find it under our assembly and then features, and we can rename that to just be plunger reference point. And that pops up in a dialog box there. So once we've got our reference point defined in our assembly module, we switch to our interaction module to create that coupling between the reference point and the face. We can use that create constraint option here. And we'll just call this plunger couple. So there's a number of different constraints that we can create here. The option that we'll choose is just a coupling. And then we'll choose that face that we want, or we'll choose the reference point that we want first. We'll call this plunger reference point so that we can use it later. And then we'll choose surface as the region we want to control, and we'll pick that top surface there. And this brings up the set of constraint dialog box. where we're just going to specify that we want to control all the degrees of freedom on that face with this particular reference point. So now we've got that set up, we can move back to that load module, and we can actually set up that that pull feature. So we'll just call this pull plunger. We'll use that displacement/rotation option. We'll switch back to that initial step. We'll select that reference point, and then we'll select all these degrees of freedom. Actually, we're going to edit that. So when we're moving this plunger, we already have that symmetry defined there on those other two sides. We've got the fixture defined. So the only degree of freedom that we're actually going to need to control is that Z direction, so that U3. So we're just going to switch that. And then on our pull plunger step, we can move to this now and edit it. And it's going to be held at 0 in every other step, but here we're just going to use a value of -25. Again, this is in millimeters to be able to pull that out. And you'll see a nice little graphical representation of your feature there too, with the arrow showing you which direction. So now we've got our materials defined, we've got our parts, we've got our steps, interactions, loads. We're all ready to go. The last thing that we need to do before running it is to mesh the assembly. And so in SOLIDWORKS, a mesh exists within the confines of each study. Each component is meshed individually within that study. In Abaqus, you can do that, but there's another option as well, which is to mesh on the part level. And so when you bring a part into an assembly in Abaqus, you get to choose whether or not you want it to be meshed at the part level or the assembly level. And if we go back and look at the assembly module here, if we go to make a new part, you can see that in the dialog box. We can choose dependent or independent. So by default, all of your parts that come in through the associative interface will come in there as dependent, which means they're going to be meshed at the part level. And what this allows us to do is to mesh the part once and then bring that mesh into the assembly. So if you had 100 bolts and you just, in SOLIDWORKS, you're going to have to mesh each one of those individually at the study level. In Abaqus, we can just mesh that part once and then bring that mesh in. And so it allows you to not only have a uniform mesh for each one of those components that you're bringing in, but it can also just be a lot faster that way. If you wanted to, if you had 100 bolts and you wanted to mesh one bolt separately from the rest, that's when you would want to mesh that at a independent level so that you could mesh each bolt separately at the assembly level. But we'll start out here at the part level through this module selection, and we'll start with the barrel. So right off the bat, the color of the part that you're looking at is basically going to tell you whether or not you can mesh it, which is a nice little interface help that you wouldn't get in SOLIDWORKS. It's the default that we're going to be meshing these parts with is just a hex, another element type that is not available in SOLIDWORKS. If you wanted to, we could just change these mesh controls to set it to TET, for example, which is what SOLIDWORKS would use, and we could mesh it as TET. But we'll take a look at some of these tools that we can use to get this to mesh in hex, which is, again, if you're moving to Abaqus, this may be one of the reasons why is because you have access to that other element type. So to mesh this in hex, what we're going to need to do is partition it. Partitions are a tool that we can use to divide the geometry into different regions. Hex elements can only be used for certain types of geometry. If you're interested in what those types are, they have a nice list and graphical representation of each in the SIMULIA help file that you can see. But we'll start out here just using this partition option here down here in the toolbar, and if we click and hold that, we can get a flyout menu where we will choose extend a face as our tool. So for the face that we'll choose to extend, we'll just choose this one here, and as we hit enter on it, you can see then that the part is going to change color to yellow, and yellow is going to mean that we can mesh this with hex. Next up is choosing an actual element size, and elements in Abaqus are going to be determined by the seed size that we've created essentially. And so if we click on this seed part option here, we can see our controls over creating those seeds. An approximate global size is just going to set, what you think approximately the size should be. We can also go in and obviously make manual mesh refinements on those seeds, but for the moment, we're just going to set this to 1 and then apply, and that should be good enough for now. And then we'll hit mesh on this, and it's as easy as that. There's our hex mesh on the barrel. So we'll come to the plunger here. We'll go through and do another partition here since we've got that same color, meaning we can't mesh it in hex at the moment. So we do that, and we see that we've got one part here, which is fine. We need to create some more partitions. And as we select this other side here, we're now going to have to select which cells we want to partition before we select that face. And we can do that just by selecting it, hitting enter, and then selecting the face we want to partition with. And we'll get one more there. And now we should be good. So we have that yellow that we've seen before. The green just means it's hex. It can be meshed by different type of hex method, but the green still means that we can mesh it with hex. So we'll move on here. For the global size, we're just going to use 0.5. And we won't apply any local mesh refinements just yet here. So we move on to the stopper, definitely a bit more complicated geometry that we're going to need to use a few more partitions, which we'll set up here real quick, using the same method that we were just using with that partition by extending a face. For this last part here, we'll actually use a different method. So instead of the face, we'll choose this define cutting plane, which allows us to define the plane that we will partition the part by. We'll select those cells, and then for the way that we want to define that is just with 3 points. And we'll just choose the 3 points that we see on that arc here. And now we've got our stopper nice and partitioned, and we can apply some global size. For this, we will choose a global size of 0.5 again, and we'll apply that. But now, if we were to mesh this, you can see the seeds there. We can see where each element would start and end with those seeds, and we're probably going to want a bit more resolution here around the bumper where this interference is going to be resolved. So let's take a look at the local mesh refinement options that you have in Abaqus. In SOLIDWORKS, you would select that face. You can specify local size. It's a similar tool in Abaqus. It's the seed edges option here. And for this, we're just going to choose the edges that we want to change the seed to. And so we're going to select all the edges here on the bumper. And since we're working with a hex mesh, we only have to choose these edges here that I'm selecting. It's then going to have to sweep those seeds essentially through that whole bumper. So that's all we need to select when we're changing those seed sizes, at least here. For the approximate size, we're just going to do 0.1. And when we hit apply, you can see that visual representation of it there. So that's how you can view any local mesh refinement that you've done in Abaqus. You can see those changes there. And once we hit OK, we can now mesh this part. And we can see now we've got a pretty good mesh on the stopper there with some refinement on those bumpers where we may need some extra cells. So if we return to the assembly object here, we get to see all of our parts with all their meshes. They've all been brought in from their dependent part meshes. And at this point, we're almost ready to go. We've worked our way all the way down the tree. The last thing that we're going to want to do before we actually run the study is to create a history output. So history outputs are used to set up queries in advance for particular things that you may be interested in. And so this allows us to specify that we want certain results at certain locations, and it prevents Abaqus from having to write entire results out. It's going to save a lot of time in addition to, obviously, space on your hard drive since you're not saving out all of those results that you may not want. So for the history output, we are going to right-click on this and hit Create. In our history output dialog box, we're going to just choose this pull plunger step, since what we're doing here is we're going to create a history output where we're going to request the reaction force on that, that reference point that we're using to pull the plunger. So we want those results in the pull plunger step. We'll hit Continue. And this is our history output dialog box. So for the domain, this tool that we can use here now is to select Set. And then there's that plunger reference point that we created earlier. And you can see now why it's easy when we can name those so we don't have to go hunting down for whatever that name was. We know that we want the plunger reference point. We can just choose it. You can choose when these are going to be saved out. So we'll just go at every 0.05 seconds, which is what we specified in our step incrementation. So we're going to get it at each one. And you can also hit out here at approximate times just in case it's through those first steps and maybe hitting something else. For those reaction forces, we can find those under Forces Reactions, and we'll just look for that RF3. So now we've got everything set up that we need to run this. We've set up the study, and we've gone through all the work. We've worked our way down the tree. We won't be doing any optimization, so we can just move on to the job module, which is where we'll create a job and then submit it for analysis. We can create a job here up the top, or obviously through the tree like we've done a few times. We'll name this job. We'll just give it the name Webinar 1. And then we select which model we want to run from. So we'll just be selecting that model that we've been working in. And this brings up the job dialog box where we'll be able to select some different options. So if it's, you can change some different options here. If it's a restart analysis, you can do that. We'll take a look at the parallelization tab here. So if you've got enough tokens available that you can run this on multiple processors here, you can make that change. If you're running this on a cluster, you can obviously bump this up quite a bit to improve the solve time. For now, we'll just leave this at 2, and we'll click OK to create that job. We can see it's then created here down in this job area. So we're all ready to go. We can go ahead and submit that for completion. We'll hit Submit, and we'll get a nice little message in our message box saying it's been submitted. And once it's running, it'll switch there to running. So while your analysis is running, you can monitor it by right-clicking on this job and going to Monitor. And this Monitor dialog box is going to give you a lot of information. You can take a look at any errors or warnings that you've got, which you've got a couple, the data file, the message file. But as your analysis starts to run, you're also going to see some of the steps start to pop up here. And so this allows you to track kind of how your analysis is progressing, to see where you are during the process. You can see if it's making multiple attempts at a step, maybe if it's an area you would want to refine. You can see them start to pop up here. You can also track what the current step time is, what your total time is, how far are you. So it's a great tool for monitoring those things, just kind of making sure that if you're not quite sure how your analysis is going to progress, that everything is going okay. For now, we will actually close out of this. The study does take a few minutes to run, so we've got a pre-run results that we can load up to take a look at. To do that, we'll just load up the results here of this syringe test 1. So you can do that by right-clicking and hitting results. You can also view the results if you just hit open here and you browse to a file. The results files in Abaqus are saved to these ODB files, and you can use these independently. And so we can load them up even if we didn't have something else open to take a look at those results. So in our results, we have some different options here again in this toolbar. You can see that now we're in the visualization module. So kind of working your way all the way down here, we're in visualization where we can view those results. We can view contour plots here. So we can take a look at the stress if we wanted to see that stress, and we can see that the analysis progressed as we would expected. This frame selector tool up here in the top right, this is a useful tool that we can use to kind of step through the analysis. And you can see here it'll give us the step that we're on, the increment that we're on, and if we zoom in here, we can see how that behaved. So initially, we were resolving that interference through a number of steps, just like we wanted to, changed the friction, and then we moved into that pull plunger step where it's going to pull that up. The final thing we want to look at is that history output that we created. If we go into our output databases, we can expand that ODB, and then under history output, we can find that reaction force that we were looking at. If we hit plot on it, we can actually see that force. And we'll take a closer look at this in a bit. It's important to note that since we're working in quarter symmetry, these results are only a quarter of what you would actually expect. So we'll look at how to modify those results in just a bit. So now we've ran our first study. We have the results. We have our simulation set up. So now the question is, how is this associative interface going to benefit us if we wanted to make a change? So let's go ahead and let's walk through that. If we did want to make a change, one of the first things that we may want to do so that we still have a copy of these current results is just to copy this model. So we'll copy this just by right-clicking and going to Copy Model. We'll just name this metaphor Webinar Modified. And now we have an additional model here. So we can see that we're in that model there, and we still have a whole copy of this model here in addition to this one. So same thing as duplicating studies in SOLIDWORKS, we can duplicate models, and everything that you created is going to come over. Now we can go ahead and switch back to SOLIDWORKS. And so let's think about making a change. So if we wanted to reduce the amount of force that was required to pull this plunger, one of the things that we could look at is reducing the size of this bumper here. If there's less contact pressure, it should require less force to pull it. So we want to investigate a change for making that bumper a little bit smaller. So we've got that change already saved here in our assembly. We can switch to this configuration called Quarter Symmetry Modified, and that'll get us, you can see there, that bumper is going to get a little smaller there. So as with before, though, it's important to point out that just changing that configuration, if we were to go ahead and export this to Abaqus right now, we're still going to get that original bumper configuration. And why that is because the stopper has still, its last save state is still in the state that it was at when it had the larger bumper. So if we want to push that change, it's important to open up this stopper and just save it in this configuration. So we've already got a configuration set up here where it's saved in that state. And all we have to do is hit save, and now we're ready to export back to Abaqus. And the last thing to point out here is just that for that change, we just used the move face operation, and so this keeps that same face ID. So if you did have any kind of specific features to find on this face, just like in SOLIDWORKS, if you don't want to break your mates, you don't want to break any simulation features you have, you try not to, blow out a whole face and then recreate it. You just want to be smart about how you're making these edits so that the face IDs stay the same, and that way all of your features in Abaqus are going to act the same as they would, in SOLIDWORKS, where as long as those IDs are the same, your features aren't going to be broken, and it's going to save you a lot of rework time. So we just use that move face command there. We'll go back to the assembly, give it a rebuild and a save, and now we'll hit that export button back to Abaqus. So let's go take a look. So this is now, remember, we left ourselves in that webinar modified model, and so this is the model that the updated geometry is going to move into. If we take a look at this, it can be kind of hard to see whether or not that change was made, so we can actually query some distance real quick just to make sure. We can use the query tool to get a whole lot of information. In this case, we'll just use the distance, and we'll just measure the distance real quick between those 2 points. And this distance that we see here, the original distance in our original file set was 1, and so we know that that change has been made. It is a bit smaller, so we can also make sure that if we move back to that webinar model, this is still that original one. So we still have our original geometry here. The associative interface is only going to push the change into the model that you're currently active in. So this copy and then push is a great way to kind of keep a snapshot of something that you've been working on earlier while retaining a new model with those changes that you want. So if we take a look at this modified model, all of our features are still there. All of our steps are still defined. Our loads, our boundary conditions are all still active. If we switch to this load module, for example, we can take a look, and all of these are still attached to those faces that they should be. So very easy to make that change and push it. The only thing that we're going to need to do before rerunning it is to just remesh it, right? So we've changed some geometry. We need a new mesh on that part. But even things like our local seeds are still there. They're still active. They're still on those edges since we used that move face. We didn't, delete that geometry and then recreate it. So everything is still active, and we can just hit remesh on this, and we've got a mesh there on the modified geometry. And so that's all we have to do before we're ready to rerun this. We can create a new job here off that new model, and we can just call this webinar modified again. And at this point, we would be ready to run that. And we would have 2 separate models then, 2 separate jobs and 2 separate results, all for those geometry changes. And it's that easy to push it. Just like you can make that change and rerun in a new SOLIDWORKS study, you can do the same in Abaqus. So hopefully it's a good demonstration on how easy you can incorporate this into your workflow while harnessing the power of both. Instead of running this, we've got some results loaded up, so we'll just go ahead and load these from this second model here. And we can see, if you did take a look at that, the max stress result available in our first one, our stresses are less, which is what we would expect. Since we've reduced that size, we've got some smaller stresses, and we should have a smaller reaction force too. So let's take a look at how we could check that with some of the post-processing tools available in Abaqus. So we have that history output that we initially created. What we could do is we could save this out. We could, take it into Excel and modify it or something so that we've got that, the 4 times. But we can also do that right in Abaqus, which is a nice benefit that you certainly would have some trouble doing in SOLIDWORKS. If we hit save as, we can just give this a name. We'll just call this Pull Plunger 1. And we can see it there. We can see the reaction force. But now what we can do, instead of taking this out, and what we could do is come down here. You can see it here in XY data. And if you wanted to, you could select Edit. And you've got a full list of the data there that you could move out if you want to do. Instead, we'll just do that in Abaqus. So if we go up here to Tools, we have a number of different post-processing tools that we can use. The one that we're interested in here is the XY data. We'll select Create. And then for our XY data, we can choose how we want to create it. So we already have some XY data that we saved out from that reaction force. We'll just choose Operate on that XY data, and this gives us this dialog box where we can operate on it with any number of functions. So a powerful tool that you can use to do this all in Abaqus instead of having to move something out. For now, we'll just multiply that by -4 just to get the full forces, and then to just the negative so that we've got some positive reaction forces. We'll choose that XY data that we already created, and then choose Save As, and just call this Pull Plunger 1. And we can do the same thing now with the other database. So if we switch to our second, just call this Pull Plunger 2. And now we have those results there. So we can take both of those, we can just Control select them, and then we can hit plot. And we'll get a plot of both of them on the same screen so that we can compare those results. We can also change those axes just like we would change a plot in SOLIDWORks. If we just double click on that, we could set up or change those axes so that we're only looking at the information that we want. And it should be coming up. We can also view multiple results right against each other. So if we wanted to see the stress results or the contact pressure and the results next to each other, we can use this viewport option. We can hit create here. We've got a second viewport, which we can then tile vertically, and then we can switch between them here. So if we wanted this to be one, we want this to be that second set that we've modified, we can take a look at those stress results right next to each other. You can see that we've got the lower stress. We can also change what kind of results we're looking at here through this toolbar. If we wanted to look at displacement, strains, or the contact pressure, we could do that. And so if you were looking at something where you needed to retain a certain amount of contact pressure, maybe to to hold whatever fluid you were in there, you could look at it through here and compare these as well, just like we were comparing those pull forward forces. So with all that said, let's take a look then at what we went through. So we've got a picture of the results up there that we looked through, just kind of as a summary of what we went over in the associative interface. The important things, at least to point out, are that it takes the last saved part configurations that you're using. The assembly units are used, so we didn't touch on that, but if you did save your parts in different units, you don't need to be concerned with that. It's just going to take your assembly units. You don't have to worry about parts coming in way oversized compared to other ones. And then as long as you're keeping those face IDs the same, just the same as you would in SOLIDWORks, your analysis features are all going to remain linked up. As far as Abaqus goes, those main differences between this and SOLIDWORks are definitely that ability to create steps, the general contact for quick global contact, using those reference points to move things around to control those degrees of freedom, and then making sure that you set up those history outputs in advance just so that you can request that data without having to save out a bunch of stuff that you don't need. So that's it for the associative interface. And then the last thing that we wanted to touch on just real quickly is this alternative method, which is called the Abaqus Translator for SOLIDWORks. The Abaqus Translator is available. It just comes installed with SOLIDWORks. You can access it once you have a study open in SOLIDWORks by going to the simulation drop-down menu and then going to export. You can then import what is brought out, which is an Abaqus IMP file. You can import that into Abaqus by going to import and then model. The translator can export a number of studies and features like the mesh. If you're more comfortable meshing in SOLIDWORks and you just want to use that, you could definitely export the mesh and bring that into Abaqus. Material properties, if you've got a really complicated material that you don't want to have to go through and recreate in Abaqus, it'll also bring that in addition to everything else listed there. Some important caveats there is that it will import your mesh as an orphan mesh, and so if you did want to make some changes to it or map it to geometry, you would have to create that geometry to map it to or go through those orphan mesh procedures. And there's no relationship with the SOLIDWORks model like there is with the associative interface. So if you wanted to make a change to your geometry in SOLIDWORks and then bring it in, it's going to import, again, just as the same input file that you would have at the start. So if you're importing these input files and then making some changes in Abaqus or setting up some additional features, you'd have to do those again for the new input file, unless it's something that you could maybe copy from the imported model into your existing one. So it's definitely got some added functionality there, but just important to know kind of when may be best to use it. And that's it for today.